flights out of SeaTac. And Alaska Airlines were canceled this morning. I'm going to go through one particular document here in the supplementary folder. We had talked about timing closure and what was involved. And we looked at a couple of different cases and we identified how you would correct that fault if you had a timing constraint violation. And on a couple of those, there was retiming of design. So this was a document that I had put together describing retiming. So it literally works by moving registers across portions of combinatorial logic to improve the delay time. There's a term here you should be familiar with called slack time, which is the required arrival time minus the actual arrival time. So in this particular case, I've got a pair of registers, some combinational logic, another register, combinational logic, and another register. Having positive slack time is a good thing, because what that means is this quantity on the right-hand side is positive. So you have this required arrival time, and the thing got there early, so you got some slack, which you can use in the retiming. So if you look at this particular example, here you have 3 nanoseconds of slack between the required arrival time and when the data actually arrived. On this side, you have lots of combinational logic, and you'll notice that the slack is minus 1 nanosecond. So that said that the actual arrival time was later than the required arrival time. So this might be caused, for example, by having too many logic levels, too many LUTs in series. So here I have minus 1 nanosecond. Here I have 3 nanoseconds. So what I can do is move some of the logic here into this logic block, or conversely, take this register and move it into this cloud of logic. So now what I've got is positive slack on both sides of the central register, because I used some of the slack time, positive slack time available here, took some logic out of here and moved it into this block. That cut the slack down to plus 1 nanosecond on this portion of the logic. But over here I went from minus 1 nanosecond to plus 1 nanosecond, so I can satisfy both requirements. Now it says, notice additional registers were added to do the retiming, but that's not a problem because the FPGA provides you lots of registers in the configurable logic blocks. So this is a little more of a concrete example of what is meant by retiming, and it defines this term slack time, which is something that you should be made aware of. What I want to talk about now is there's a couple of videos. One is a video that's almost an hour. We're not going to look at all of that, but there is a short 9-minute video that I want to look at, and that's the notion of microblaze. This is a term that you may have heard or may not have heard. It's a microprocessor that is actually built out of Lutsen registers. If you go back and you look at the data sheet when we talked about the Vertex 5, there was only the FXT series that had as hard IP PowerPC microprocessors that you could instantiate and use, and they were external to the FPGA fabric. This microblaze is built specifically out of Lutsen registers and can be implemented on any FPGA that Xilinx makes. I think it even goes back to the Spartan series, which came out a little over 15 years ago. The second video talks about the microblaze microcontroller, which is a scaled down version of the microblaze. The microblaze is an actual full-blown, in every sense of the word, microprocessor, runs at several hundred megahertz clock speeds. The microblaze microcontroller is a scaled down version, and like all microcontrollers, if you compare those to the microprocessors, the microcontrollers are set up for doing input-output operations, so they have input-output ports on chip and so forth. So, the microblaze controller. Stand by a minute. Never find anything when you need to. Generally only have the microblaze itself, the microcontroller. Okay, so I guess we'll look at that.
But my control.
It gives you the same
way to add a microcontroller, but now there's no FPGA-based logic project. It's a leaner, trimmed-down version of
Right.
Studio. It gives you the same microBlaze processor, the same performance, the same device support, but now there's no longer a need to obtain an embedded design license. There's no need to learn an additional tool like XPS. It includes a very general set of solutions. I'll be spending a bit of time today talking about a product called microBlaze Microcontroller System. What exactly is it? Well, it's a quick and easy way to add a microcontroller to any FPGA-based logic project. It's a leaner, trimmed-down version of our popular microBlaze microprocessor without the need for Embedded Design Kit or EDK, Embedded Edition, or Xilinx Platform Studio. It gives you the same microBlaze processor, the same performance, the same device support, but now there's no longer a need to obtain an embedded design license. There's no need to learn an additional tool like XPS. It includes a very general set of processing peripherals, which we'll look at, and it's supported by the software design kit from Xilinx or other Eclipse-based software design tools like GNU GCC. And it's available starting with the 13.4 release of both the ISC Logic Edition and the free ISC Webpack Edition. In short, it's an ideal solution for microcontroller-based design. So how would I configure and use microBlaze MCS? Well, microBlaze MCS consists of three major components. The first is the microBlaze processor. It is pre-configured for three-stage pipeline mode, and the options are pre-configured as well. Peripheral assembly called the I/O module, which we'll look at in a little more detail. And finally, an easy-to-use configuration wizard that wraps the two together and helps you place it in your design quick and easy. And then just 3 steps to use microBlaze microcontroller system as well. First, you place it in your project through the IP catalog. You configure microBlaze MCS through the wizard, and you're ready to begin coding your software. So that's enough of the slideware. Let's look at a demo and watch it in action. I'm starting this project from PlanAhead, which is our ISC logic-based.
Okay. A couple of terms he had in there. He talked about EDK. EDK is a embedded design kit, EDK. And I'm going to be discussing a little bit about that after this video. EDK is a complete software tool. It's like doing synthesis. You have to define a project, define all your modules, et cetera, and it kind of takes you through building an embedded system. This microcontroller does not require you to use EDK to build up your embedded system. So he's going to show you a shorter version of this.
Program manager and design manager. If I was an FPGA logic designer, this is more than likely where I'd be starting from in a Xilinx project. I'm going to open up an example design. The smallest one of these is called BFT Core. And by the way, these example designs, the one I'm using today, all come pre-installed with ISC installs. So you can come back and replicate what I'm doing here. And I'm also running from a Webpack license, which is our free downloadable license. So you can literally download the software, download the license, and be replicating what I'm doing right here in this demo. We're going to save it to my own directory just so I can muck around with it. We'll call it Project 2. And you'll see that my BFT project is now opened up in the hierarchy manager. I can now go look at the HDL. I can go open up any one of these, go edit it. You'll also see a couple of cores down below that were placed using our IP catalog called Core Generator. And we'll talk a little bit about that in just a second. Now, at this point, if I wanted to add a full-blown microBlaze, I would normally do an add source and say add or create embedded design sources. And when I said next and finished, it would go open up another tool called XPS. And that tool lets you do things like set up interrupts, set up your register space, pick from a whole slew of peripherals. But remember, what we're dealing with today is Microblaze MCS. All I need to do here is go open up the IP catalog. A lot of the glue logic or simpler functions have already been created for me in this IP catalog. And by double clicking, I can then go add things like an adder subtractor, a FIFO, things that I really don't want to have my designer spend time on. But if I go open up this embedded processing part of the catalog and then go select processor, there's Microblaze MCS. Let's go double click that. And you'll notice below in my details section, I get a description of the core, I get links to things like data sheets. I can also see what's changed in revision to revision. We basically give you the info you need to go analyze that core. So here's the configuration we discussed earlier. You'll notice on the
Now, one of the things that you're gonna notice on here is he's going to go through those tabs up there and select different options. He's going to customize this microcontroller system. And as he selects different features, what's gonna happen is the stuff that's in light gray shading will light up, indicating that those particular features or capabilities have been added to the core based on options that you select.
Assembled, and on the right, all my configuration parameters. Notice we have the UART, we have up to four fixed interval timers, up to 4 programmable interval timers, general purpose outputs, and general purpose inputs, and also a set of interrupts. And again, this is that basic I/O module that we discussed. For this design, let's go enable the UART, let's go turn on one of the fixed interval timers, and let's go turn on one of the programmable interval timers, and we'll change the bit width down to 16 bits. So you can see, highly configurable, very easy to use. I'll turn on one of the GPOs for output,
Yeah, see
and
how this
again
stuff
change
lights up?
the bit width to 24 bits. So you can see I'm doing this all through the wizard. Excuse me. You'll also see that my symbol is changing as I'm adding different options or taking away different options. And we'll just stop at this point and say generate. And now the configuration wizard drops that core into my design. And there it is. So let's go over to IP sources. Let's go expand this, and let's go add an instantiation duplicate. And say generate that. And then quickly I get what I need to go be able to copy this into my top level HDL so I can go place this correctly in the hierarchy. Let me go double click that file, and there's everything I need to go place Microblaze MCS. There's the different options the way we configured it. So now I can go cut and paste this, put it where I want in the hierarchy. Basically, I'm off and running, I'm ready to use it, just as easy as we discussed. To begin wrapping up, a quick review of Microblaze microcontroller system features. First is it's included free with ISE Webpack, and it comes included with the purchased ISE Logic Edition. Again, those are versions 13.4 or later. It does have the fixed peripheral set we saw, and the processor has been locked down to 3-stage pipeline for leaner microcontroller configurations. The peripheral set, if you need to use memory, it does support local block RAM using the FPGAs from 4 kilobytes up to 64K. If you need streaming ports, you'll want the full Microblaze, but both versions support Microblaze debug modules, so you can do debug. If you need AXI4 streaming, or you need AXI4 bus connections, you'll need, again, full Microblaze. And both versions are supported by the Xilinx Software Development Kit, otherwise known as SDK, or other Eclipse-based software tools like GNU GCC. The value to you, the customer, is that Microblaze MCS offers high programmable systems integration. This product works with any Xilinx FPGA, including our new Zig 7000 series. as long as you have the design logic space available. And it is high performance. It's the same performance as our full microblaze product, over 300 DMIPS performance in the leading Xilinx logic families. It helps you reduce BOM cost by bringing in, again, a very streamlined microcontroller with an included I/O peripheral packet, so you don't have to go add more IP. And it does support total power reduction. It's an ideal footprint for low power applications. And we didn't talk about it, but Microblaze supports a sleep mode instruction. So you can turn off Microblaze and Microblaze MCS and attach logic. And finally, accelerated design productivity. Very high flexibility. It lets you support a wide range of applications. And we didn't really talk about it in detail, but Microblaze MCS is included with our new Bravado Design Suite as well. So thank you for listening. If you'd like more information, please visit Xilinx.com. Either of the two links I show here for Microblaze microcontroller system or for Microblaze. And you can download either our free Webpack edition or purchase the Logic edition, and again supported in versions 13.4 or later. And if you try out the new Bravado Design Suite, you will find Microblaze MCS there as well. Thank you.
Okay, so let me set up this. So we're working in a sense a little backwards, but so the Microblaze microcontroller I'm going to use MuC for microcontroller. Is targeted for embedded system applications. And I'm going to define an embedded system system where the computing resources are incorporated into a product. And I'll put down as a note, because this is a characteristic of embedded systems. In embedded systems, the end user may not be aware that they are actually working with a computer. One of the examples I like to use to illustrate this is a photocopy machine. If you walk up to a photocopy machine, you'll typically find some little keyboard where you can enter in very rudimentary information. There might be some simple little liquid crystal display. You can choose how many copies you want. You can state whether you want to zoom in, whether you want the thing collated, stable, double-sided printed, and so forth. And then you hit the start button. But there's an actual computer in there that decodes the keyboard, turns on the motors to move the paper through the machine, adjusts the lens to do the zoom in or zoom out, whichever you wanted. All of that stuff is done, and the user is not aware of the fact that they're actually working with a computer. One of the characteristics of embedded systems actually, we can list several of them. These embedded systems tend to be I/O intensive. They do a lot of input and output operations. If you look at standard desktop computing environments like this one here, relatively little amount of time is spent doing input-output operations. In embedded systems, that is one of the primary functions, and I'll show you a block diagram for a typical embedded system shortly. They tend to have low clock speeds compared to desktop computing systems. You'll notice I'm kind of taking a broad category of desktop computing systems like this here and an embedded system. My iMac has a clock speed of, I think it's 3.2 gigahertz. On a lot of embedded systems, the clock speed is under 20 megahertz. And stop and think about this for a moment. In your home, how many are aware of the fact that your washing machine is an embedded system? Small computer in there that decodes the entries that you put on, turns on the valve to fill the thing up, detects when the water level is sufficient, turns it off, turns on the motor to turn the basket, and so forth. So it's under computer control. That probably does not have to run with a clock speed of several gigahertz, doesn't need gigabytes of memory like a desktop computer might. So the 20 megahertz is probably more than adequate for the washing machine. So it's low clock speeds. Small memory. The MicroBlaze microcontroller can communicate with a fair amount of memory. When I talk about small memory, a lot of processor chips designed for embedded applications have all of the memory on chip. There's no external memory interface. You might have 80 bytes of RAM. I didn't say kilobytes or megabytes, 80 bytes of RAM. You might have 1K of flash memory. That's it. But that's not a restriction because it has a small number of dedicated tasks. Consider that microcontroller that is running your washing machine. It's only a handful of tasks that it has to do. And that ties in with this next bulleted item. Cannot be reprogrammed by the end user. microcontroller that has been programmed to do the task associated with running a washing machine cannot be reprogrammed to do word processing or play first-person shooter video games or something like that.
I saw somebody reprogram a photocopier to play Doom the other day.
Yeah, but that's kind of a jailbreak type of thing as opposed to,
And it has a screen. Washing machine doesn't have a screen.
yeah, but it doesn't have a screen. But in general, unless you jailbreak the thing, it can't be reprogrammed by the end user to do some other set of tasks. And this is, these last two may be rather surprising. The most common programming language is, want to take a guess?
See?
C, not C++.
Although that is changing.
Actually, it's not. If you go and you look at the literature, the cyber physical systems that have been coming out now, C is still predominant. It goes far beyond what Python and Java and whatever of these other ones are. Talking about the low-end microcontrollers where you have only a few hundred bytes of programmable memory, C is still predominant. Microcontroller versus microprocessor sales. Sale of microcontroller chips has exceeded that of microprocessor chips by huge amounts. First time that the microcontroller sales exceeded the microprocessor sales was 1999 and has every year since then. I think that's one of the problems that Microsoft ran into about 10 years ago was they were so tied to desktop computing systems. They kind of missed the boat a little bit when you started coming out with more and more embedded type systems, portable systems, iPhones, iPads, tablets, and so forth. So they were a little bit behind the game on that. But this is something that's been true for more than 15 years. Okay, so now, let me set up context for embedded systems in FPGAs. All right, so let's see. Here's your FPGA fabric. Here's some hard IP. We'll assume that this is one of the FXT Vertex 5s. So we've got a couple of PowerPCs available. We have block RAM and we have DSP slice. Got some IP, and let's say some third-party IP. That'll go here into the fabric. There's your application software. This has to go through compiler, linking in other libraries, etc., and a loader. And that has to go into, let's say, block RAM for execution. Microprocessor will then read its instructions out of block RAM. Some of the block RAM may be used for data memory, or let's say, here's some distributed RAM that the microprocessor also has to have access to. Okay. So we know how to write our own IP. We know how to take third-party IP and take the files that the third-party IP vendor will provide to us and incorporate that into our design. We know how to instantiate the microprocessor, which that's going to have to be done. We can infer block RAM. We can also infer distributed RAM. We can write our code to perhaps infer assets out of the DSP slice. On the software side, we're going to write our application software. It then has to be compiled, etc., and be stuffed into block RAM. The question is, how does all this come together? Because if you stop and think, how do you program this FPGA? Well, you have a file, a bit file on the computer, and it gets downloaded through the download cable into the FPGA. It can be either directly program the FPGA, or indirect programming. It can go through the FPGA and program some sort of non-volatile memory on the board, and then the FPGA can get its configuration information out of that. So how does all this get tied together into a single bit stream for programming the FPGA? Now, this framework that you see here is typical for an embedded system. You have your processor, you have some cyber portion in here, you have your IP that'll do whatever processing of data needs to be done that is done in hardware as opposed to software instructions, and you have your application code. Well, let's do this. We have the hardware design, and this will entail stuff like the IP design, Maybe using the Microblaze MCS as part of your design.
You're off the screen a bit.
And so forth. And let's call this the hardware bit stream. Then over here, we have the software design. We're going to go through a compiler, some sort of linker loader. And this will give us, this will be the executable code coming out of here. So let's call this the software bit stream. Now the FPGA manufacturer is going to provide you with a utility. And for Xilinx, it's called Data2Mem. And it takes the hardware bit stream and the software bit stream and merges them to give you your .b or .bit file, your data stream that you download to the FPGA. So your hardware designers can work independently, your software designers can work independently, at least through a certain portion of the phase. But then when you're ready to put everything together, you need to get to the appropriate utility that will merge those two bit streams together to create the single bit stream, which gets downloaded into the FPGA. Now the thing that's nice about some of these utilities that have come out recently is they allow you to debug your software and create a new bitstream file without starting each time from scratch. If you stop and think about it, your hardware design, once it's been finalized and tested, this portion here is pretty much going to remain fixed. But you're debugging your software, you're redoing the software to correct bugs, deficiencies, what have you, while this portion remains fixed. Rather than start and have to recreate both bit streams, what some of these utilities allow you to do is to fix this and then only reinsert in the new software bit stream and then create a new bit file without requiring you to start at the beginning, define your project, and do all of that stuff, so you only have to do it once. So it really cuts down the amount of time it takes to debug and verify your software. So this is the type of design environment that you're going to be looking at when you are developing these embedded systems using FPGAs, which incidentally are an ideal application for the FPGA.
Just to verify, so the hardware is described in HDL, and then the software is like whatever is going to be running on that hardware?
Yes. Okay, on this hardware design process to get the hardware bit stream, you're obviously going to have IP that you write, and you may have some second-party and third-party IP. You're going to use the Xilinx Wizard, that generation tool, to create your Microblaze microcontroller system. And that all then gets merged into the hardware design portion. But what's missing out of that, and we know how to do that, creating black boxes, which are necessary. But what's missing out of that, and has to be incorporated in the bit stream, is the executable code. So that's what the purpose of this particular utility is. It's called Data to Mem. For Xilinx, Lattice calls it something else, Attel calls it something else. But that's the utility you need to look for to merge those two, to create a single bit stream for your embedded system. When we took a look at the synthesizer software, one of the options that we had was to choose multiple languages for the hardware description language. And I need to go back and find this where it was put. So bear with me a moment. Can't seem to find what I'm looking for. Can't find it. I had some notes that I had put together on System Verilog to give you a brief introduction to System Verilog. But some reason I can't, can't find it. No. Okay. The last thing I want to cover, this is something that was discussed in several of the videos that is unique to the Xilinx FPGAs. And I do want to discuss this so that you will understand what the term means. They talked about shift register LUTs, SRLs. And you may have come across that term numerous times and not really understood exactly what this is. And this is something that is unique to Xilinx. If you look at the LUTs, you tend to find that they are rather small. They're like 16 by 1. You get 16 memory locations and only 1 bit of data stored in the location. So actually, what it looks like is simply that. This is what your LUT structure looks like inside these configurable logic blocks. This is an example of a 16 by 1. You just have 16 D flip-flops, and then you have a multiplexer. The address that would come into the LUT selects one of those 16 registers, and that's the data that comes out. So it's not an actual memory chip in the conventional sense. Because it's just 1 bit of data, you only need as many registers as locations, and then you need 1 big multiplexer, and the select lines of the multiplexer are driven by the address line, and that's how you get your data. So that's the LUT structure. Now they exploit that in the following way. This is the shift register LUT structure. Now, when you have a shift register LUT, what you're doing is you're implementing your shift register in a LUT. It's the name shift register LUT. And we'll look at the code to infer that in just a moment. You'll notice that it looks almost the same as your LUT structure. The difference is you now have connections from Q to D, Q to D, Q to D, so you formed a shift register. And it says down here, note, when you've inferred a shift register LUT, and you can instantiate one because it is one of the IP that's available in the library that Xilinx provides a second-party IP. When it's configured, those connections are automatically added. Now, bit 15, the most significant bit, is the single output, because this assumes that you're doing a shift register, and you could perhaps parallel load in the data, so you're doing a parallel to serial conversion. But coming out of the most significant bit is the only normal data output. But here's what's nice about the shift register LUT structure. I've hooked all of these together into one big shift register. And it's a 16 by 1 shift register LUT 16. So it's a 16-bit register. Let's suppose I want a 5-bit shift register. Well, I can hook this up It operates like a shift register, except what I'll do is I'll put in 4 for the address lines. And what comes out through the data? That Q. So you can get, with the SRL 16 structure, a 2-bit shift register, an 8-bit shift register, a 12-bit shift register. The address here will just pick the tap-off point, and that's what comes out through the data line here. Okay, everybody see how that works? So it's necessary that you form the connections from Q to D so that you get the shift register structure. And then the address that comes in determines how many bits you want in the shift register. Now, as far as inferring the shift register, sorry, that's it for I put together this document. So it says, when a shift register is described in code, the synthesis tool infer the use of a SRL16 component. This SRL16 does not have either synchronous or asynchronous set or preset inputs and does not have access to all bits at the same time. You can get a cascadable version if the shift register is more than 16 bits. Now, notice the second paragraph. Adding a reset is one way to force the synthesis tool to use flip-flops in the FPGA fabric rather than a shift register LUT. So if you want to put a clear on your shift register, it's going to implement it in the FPGA fabric, which means you're going to start using up registers. Because if you want a 16-bit register, you're going to use up the registers from several configurable logic blocks to build it. If you do it as a shift register LUT, it's actually implemented in block RAM. And it is faster and requires significantly less space. It says the shift register LUT does not have a parallel load capability. An equivalent function could be implemented simply by anticipating the load requirement and shifting in the proper data. So here is the code that you would use to infer a shift register LUT. It's rather simple. Always at the positive edge of the clock, Q, and this is an intermediate value, is equal to, and what does this concatenation operator do? It shifts everything over by 1 bit position and then inserts into the least significant bit your new data. And then you have a second always loop where Q is set equal to the 15th bit. So the second statement is needed because Q15 is the output of the shift register LUT. Q internal is only a internal variable, just to keep track of what the shifted value is. So this is your shift register LUT code.
So how would you do a serial to parallel?
I'm sorry?
How would you normally do a serial to parallel shift register?
Well, this the shift register LUT here will not do a serial to parallel for you, because you only have access to one bit position. All the shift register LUT does is, through that multiplexer, it determines how many bits you want, and that's the one bit that comes out. It forms a 16-bit shift register, but the multiplexer allows you to tap off at the 5th point, the 9th point, the 12th point, so you can get a shift register of any length less than 16, and it's all implemented in hardware. So, yes.
So I did have a question about that. In that code example, we hard coded in the 14 and the 15.
Yeah.
Would the Verilog automatically, it wouldn't automatically generalize that for us
What do you mean?
in terms of having that MUX where you could choose which one outputs and things like that.
No, what that does is that creates the shift register LUT. The shift register LUT itself needs to have an address that comes in. So all this does is just infer that a shift register LUT needs to be built. But the shift register LUT itself does need an input in addition to data. It also needs an address so it knows how many, what the tap off point is.
Oh, okay. So when we do this, it will then look at that 14 or 15 and choose
Right.
how to implement it. Oh, okay, gotcha.
That's funny. It's not, the announcement is on there. I'll have to look at that. Anyway. I'm gonna go over homework 8. Homework 8 is going to require you to take a small project and implement it from start to finish. This is the specification. You're gonna have to write the code to describe it. You're going to have to simulate it, which means you're going to have to write a test bench to test it. You're then going to have to simulate it, and then you're going to have to synthesize it. And then it's going to have to be demoed. And on Thursday, the TA will be telling you what the schedule is for demos. She's gonna have extended hours, because this is not team-based, this is individual-based. So you're gonna have to individually do this. Okay, you're gonna be implementing a barrel shifter. A barrel shifter is a sequential circuit with N data inputs, N data outputs, and a set of control signals that specify how to shift the data between the input and the output. You're going to be building a 5-bit barrel shifter. So the barrel shifter is going to take 5-bit data input, and then it will either shift or rotate by an amount S, which is a 2-bit input. 4-bit input opcode will indicate the operation. So there's your 4-bit opcode. This letter A, as the note says, is 0 if you're going to do a logic shift or rotate. It'll be a logic 1 if you're going to do an arithmetic shift or rotate. What's the difference between logical and arithmetic?
Give the sign bit.
Whether or not you take the sign bit into consideration. For arithmetic, you have to. So you can left rotate. There's your opcode for right rotate, left shift, right shift, load in new data, and no change. No change meaning if this is the opcode that you have input, you could sit there and clock the thing from here till eternity and nothing changes. This X here is a don't care. Obviously, if I'm gonna load in or not change the data, it doesn't matter, if the most significant bit is 0. Yeah,
For the one that says 0 into MSB, if that's a negative number, would that be a 1, or is that only shift to 0?
I'm sorry?
If the number that's in there is negative and we want it to be an arithmetic shift, would that shift in a 1?
The arithmetic shift will preserve the sign, it just changes the value, the data value, which is the remaining bits. So you're shifting in a 0. So it does the normal shift, which would multiply by 2 or divide by 2. But the sign bit does not change. So when this says MSB, what it's talking about is for the data value, you're not supposed to change the sign if it's an arithmetic shift. So you're actually shifting into the second most significant bit if you're doing a shift, right? Does that make sense? Yeah.
So if you're loading new data, where, what input ports are we loading the data?
Oh, I haven't got there yet.
Oh,
So does everybody understand the opcodes? Okay. S is another input. And for these values, this will tell you if you're gonna shift or rotate 1 bit, 2 bits, or 3 bits. Okay. Okay, there is the rough numbering of your 7-segment displays. The data, opcode, and shift amount should be input through the slide switches on those demo boards. Use a push button to execute the desired function. That is, pressing the push button switch, that should be once, not 1, is equivalent to applying 1 clock pulse. So you're gonna have to detect when the switch comes in, and that will be equivalent to 1 clock pulse. So with this numbering scheme for the 7-segment displays, these two are used to show what the output is from your barrel shifter. These two will be the input that you apply. S4 will be the shift amount, so that'll be 1, 2, or 3. S5 and S6 will show the opcode. Now, obviously, those are binary. You're going to be displaying decimal. And then S7 is not used. Also, you should display the barrel shifter output, opcode, and S-bit using the onboard LEDs. And use the same convention. We were using S0 and S1 for the output, which you can display in decimal. You're gonna require 4 bits, 4 LEDs for the, when you display the output in the LEDs. So you use L0s through, you have a 5-bit output that should be, yeah, L0 through L4 will be the output. Then your input is 2 bits, so you'll use the next 2 for the input, and so on. So everybody's using the same display format in terms of the LEDs and 7-segment displays. Your design, simulate, and synthesize this design. Make sure your simulation does an exhaustive test. Everybody knows what an exhaustive test is. Everything in here has to be checked for every possible option.
including 0, 0 on the.
Say again?
Including 0, 0 on the, since we can only ship to 1, 2, or 3.
I cannot hear you.
Oh, sorry. Including testing for things that shouldn't ever happen, like 0, 0 in the function, the blue thing right there.
That's not an exhaustive test, it's an invalid input. Those are the only valid inputs.
Okay. So invalid inputs aren't part of an exhaustive test.
Exhaustive test means if I'm going to do a left rotate check, I do a left rotate check for all 3 values of shift. So what you will then do is turn in your source code for the design and the test bench, along with the simulator timing diagram. And then you're gonna have to demo it, and the TA will let you know on Thursday what her extended hours will be, yeah.
So when we did the initial thing, where we demoed, we just kind of loaded that code you gave us. Is there any resources that help us set, beyond the user manual to help us understand how we're supposed to set up the inputs and outputs? And
Well,
how those
I
work?
believe out of the code that you had for the synthesizer, there's, you can look at that code and see how to access the LEDs and 7-segment displays.
Well, in the code they access it, but it looked like when you go into the studio, you need to actually use the GUI to somehow map things like pins to the variables or something, and I didn't understand.
You can use the same thing that was done in the synthesizer code. That should be your, I hate to use the word template, but that design that you synthesized had to use the displays and everything.
But it didn't use the LEDs, so like how are we gonna figure out, like how are we?
If there's some, I'm gonna have the TA look at this, and if there's some additional information, that's gonna be required for the LEDs and or the switches, I'll make her aware that she needs to put together something that she can provide to you.
Okay.
But the LEDs should not be a problem.
Yeah.
I'm sorry, the
The
7-segment
second,
displays. Okay, does everybody understand what's required on this?
And then can we use that segment, 7-segment display code from that, or should we
Yes.
write our own? Okay.
Yeah. No point reinventing the wheel.
Yeah,
If
yeah.
you see something in there that would be useful, such as drivers for the 7-segment display, if there's a driver module in there, by all means, feel free to use it. Yeah,
When's it due?
I'm sorry?
When's the assignment due?
This will all be due next week, before the final.
Thursday?
And she will, let you know on, Thursdays, she will come in here and let you know what hours, extended hours she's gonna have for demos. Again, you should do this ahead of time. Your simulation's all been done and you've got your timing diagram. You're coming in just to do the demo, so you've got a memory stick with the bit stream that you just download, do the demo, and then you're out of there. Any questions? Okay. Thursday is your second test. Yeah.
I'm asking probably for more here, but can you have it due on the day of the exam?
Can
Because-
what?
Can you have this homework due on the day of the exam? I know I'm asking for a bit more, but there's like a lot, we have.
You mean the final?
Yeah, can you have this due on the day of the final?
Oh.
Final's due on Tuesday. I mean, we demo with,
Uh,
I don't know. like-
yeah, you can turn this all in on the day of the final.
Okay, I appreciate it, thank you.
Your final is on a Tuesday?
Yeah, Tuesday.
I've got 2 finals to give, and one is Monday, one is Tuesday, I'm not sure which one.
Let me put the check.
Let's put it this way, whatever the day is of the final in here, that's when you can turn this homework in.
Okay. Okay.
As a matter of fact, I don't think I put a due date on there, but we'll make it the day of the final.
Okay, thank you.
Good question.
Yeah, because we got like 3 homework.
Yeah, that's what I was thinking, I was like, oh, yeah.
Yeah,
So,
I got another class, 2 homeworks, like, only got like 5 homework in 1 week. That's it.
We're gonna get started on this.
Don't worry.